For most of human history, the universe appeared to be a place of dependable order. The sun rose each morning, seasons followed one another in rhythm, and objects behaved in ways that could be predicted with confidence. This everyday experience shaped the earliest scientific thinking and eventually hardened into a powerful assumption. Nature is governed by precise laws, and if those laws are known, the future can be calculated. By the 17th century, this idea became the foundation of classical physics, especially through the work of Newton, whose equations suggested that the universe functioned like an immense machine. Every motion had a cause, every cause produced a predictable effect, and uncertainty existed only because human knowledge was incomplete. This classical vision of certainty reached its philosophical peak in the belief that reality itself was fully determined. If one could know the position and motion of every particle at a given moment, then the entire future of the universe would unfold with mathematical inevitability. There was no room for genuine chance, only complexity. Randomness was seen as a temporary placeholder, a sign that measurements were crude or information was missing. Given enough intelligence and precision, uncertainty would disappear. The universe, in this sense, was readable, transparent, and obedient to reason. Few scientists embodied this conviction more deeply than Albert Einstein. Although he transformed physics by showing that space and time were flexible rather than absolute, Einstein never abandoned determinism. For him, the beauty of nature lay in its rational structure. Laws were not statistical guesses. They were exact statements about what exists. When outcomes appeared random, Einstein assumed that deeper variables were hidden from view, quietly preserving order beneath the surface. To accept true randomness, in his mind, was to accept that reality itself was incomplete or irrational. This confidence in certainty began to crack in the early 20th century, not because classical physics failed at large scales, but because it collapsed when scientists examined the smallest building blocks of matter. Experiments involving light and atoms produced results that could not be explained by deterministic laws. Energy appeared in discrete packets rather than continuous flows. Particles behaved like waves, and waves behaved like particles. Most disturbing of all, outcomes could be predicted only in terms of probabilities, not certainties. The decisive rupture came with the realization that uncertainty was not merely practical, but fundamental. This idea found its clearest expression in the work of Werner Heisenberg**, who demonstrated that certain properties of particles cannot be precisely known at the same time. Position and momentum, for example, are linked in such a way that increasing certainty about one necessarily increases uncertainty about the other. This was not a technological limitation. No improvement in instruments could overcome it. Nature itself imposed the restriction. Here, classical certainty met its limit. The universe was no longer a machine revealing its inner workings to any sufficiently careful observer. Instead, reality appeared to resist full description. Measurement became an active process rather than a passive one. To observe was to disturb. The very act of trying to pin down a particle's position altered its momentum, not accidentally, but inevitably. Knowledge was no longer detached from what was known. This realization overturned centuries of intuition. In classical physics, uncertainty belonged to the observer. In quantum physics, uncertainty belonged to the world. The laws of nature no longer described what must happen, but what is likely to happen. A particle did not travel along a single, well-defined path. Instead, it existed as a range of possibilities until an interaction forced a specific outcome. Reality, at its most basic level, was not a fixed script, but a set of probabilities waiting to be resolved. To many physicists, this was not merely unsettling, but deeply counterintuitive. How could the universe function without certainty? How could nature rely on probability and still produce stable structures, stars, planets, and life itself? The answer emerged slowly. Uncertainty at the microscopic level does not destroy order at the macroscopic level. Quantum randomness averages out, giving rise to the reliable patterns we experience every day. The solid ground beneath our feet exists not despite uncertainty, but because of it. Still, the philosophical cost was high. Classical certainty offered comfort. It suggested that the universe made sense in the same way a well-written equation makes sense. Quantum uncertainty replaced that comfort with ambiguity. It suggested that there are limits to what can be known, not just in practice, but in principle. Some questions no longer have precise answers, not because science has failed, but because reality does not provide them. Einstein resisted this conclusion to the end of his life. He acknowledged the mathematical success of quantum mechanics, but rejected its interpretation. For him, probability could not be the final word. He believed that future discoveries would restore certainty by revealing hidden variables beneath quantum behavior. History, however, moved in the opposite direction. Experiments consistently confirmed quantum predictions, and attempts to reintroduce classical determinism grew increasingly constrained. What emerged was a new understanding of certainty itself. In the quantum world, certainty does not mean exact outcomes. It means exact probabilities. The laws are precise, but what they govern is likelihood rather than inevitability. Nature does not promise a single result, only a structured range of possible results. This subtle shift marks one of the deepest revolutions in human thought. Classical physics taught us that the universe could be known completely, at least in principle. Quantum physics teaches us that the universe can be known accurately, but not exhaustively. There is a difference between knowledge and control, between understanding the rules and predicting every move. The transition from certainty to uncertainty is not a collapse of reason, but an expansion of it, forcing science to accept that mystery is not always a sign of ignorance, but sometimes a fundamental feature of reality itself. From the moment Albert Einstein entered the world of physics, his guiding belief was that nature must be intelligible, orderly, and complete. To him, the task of science was not merely to describe observations, but to uncover the deep structure that made those observations inevitable. This conviction shaped every major contribution he made, from special relativity to general relativity, and it remained unshaken even when the foundations of physics began to tremble under the rise of quantum mechanics. Einstein's faith in determinism was not stubbornness for its own sake. It was rooted in a philosophical vision of reality that he believed science could not abandon without losing its meaning. In Einstein's view, the universe was governed by laws that existed independently of observers. Reality did not wait to be measured in order to exist, nor did it change its nature based on how it was questioned. The moon, as he famously remarked, was still there even when no one looked at it. This belief placed Einstein firmly in the tradition of classical realism, where physical properties have definite values whether or not they are observed. Measurements in this framework reveal reality, they do not create it. This stance was reinforced by Einstein's greatest achievements. Relativity did not introduce randomness or uncertainty into nature. On the contrary, it replaced older ideas with even more precise laws. Space and time were no longer absolute, but they followed exact mathematical relationships. Gravity was not a mysterious force acting at a distance, but the curvature of space-time itself, governed by elegant equations. Every effect followed from a cause, and given sufficient information, outcomes could be predicted with absolute certainty. To Einstein, this was how successful physics should behave. When early quantum theory began producing probabilistic results, Einstein initially treated them as provisional. He accepted that the theory worked, but he did not believe it was complete. Probability, to him, signaled ignorance rather than indeterminacy. If physicists could only see deeper, beyond the surface-level equations, then certainty would return. There must be hidden variables, unseen elements of reality that determined outcomes precisely, even if current theories failed to describe them. Einstein's resistance was not emotional, it was logical. He believed that a physical theory should describe what exists, not merely what is observed. Quantum mechanics, in its standard interpretation, seemed to abandon this goal. It spoke of wave functions, probability amplitudes, and measurement outcomes, but it refused to say what a particle actually was doing before it was measured. For Einstein, this was unacceptable. A theory that could not describe reality independently of observation was, in his words, incomplete. This concern reached its sharpest expression in Einstein's objections to non-locality. Quantum mechanics implied that particles could be entangled, sharing a single quantum state even when separated by vast distances. Measuring one particle appeared to instantaneously affect the other, regardless of the distance between them. Einstein famously dismissed this as spooky action at a distance. To him, it violated the very spirit of relativity, which forbade faster than light influences. Determinism was not the only principle at stake. Locality and causality were also under threat. Einstein's response was not to reject quantum mechanics outright, but to challenge its interpretation. He believed that the strange features of the theory arose because it was incomplete, not because nature itself was strange. If hidden variables existed, they could restore both determinism and locality, preserving a coherent picture of reality. This hope culminated in thought experiments designed to expose what he saw as contradictions within quantum theory. What made Einstein's position especially compelling was that it was grounded in a broader philosophy of science. He believed that the goal of physics was to describe an objective reality that exists independently of human perception. Without this assumption, science risked collapsing into a mere catalog of observations, disconnected from any deeper understanding. Determinism, in this sense, was not just a technical preference. It was a safeguard against relativism and subjectivity. Yet, as quantum mechanics matured, it became increasingly clear that Einstein's expectations were not being fulfilled. The theory's predictions were tested repeatedly, and each time nature sided with probability rather than certainty. Experiments involving entangled particles confirmed correlations that could not be explained by local hidden variables. The universe behaved exactly as quantum theory predicted, even when those predictions violated classical intuitions about cause and effect. This outcome did not diminish Einstein's legacy, but it reframed it. His objections forced physicists to confront the philosophical implications of quantum mechanics rather than dismiss them. Without Einstein's relentless questioning, debates about realism, locality, and completeness might have remained vague or superficial. He acted as the conscience of physics, insisting that success in prediction was not enough, that understanding mattered. In retrospect, Einstein's belief in determinism appears less like an error and more like a boundary marker. It defined the edge of classical thinking and highlighted just how radical the quantum revolution truly was. By refusing to accept probability as fundamental, Einstein clarified what was being lost and what was being gained. Certainty was giving way to statistical lawfulness, and reality was no longer a fixed script but a landscape of possibilities. Einstein never stopped believing that a deeper, deterministic theory might someday emerge. History has not fulfilled that hope, but it has shown that his challenge was essential. His insistence on hidden order sharpened the questions that quantum mechanics raised and ensured that they would be taken seriously. In confronting Einstein's vision of determinism, modern physics did not merely reject it. It learned to define itself against it, recognizing that the universe might be profoundly lawful without being fully predictable and deeply rational without being completely determined. In the early 20th century, physics reached a point where asking deeper questions no longer produced clearer answers, but sharper limits. This turning point did not arise from philosophical speculation alone. It emerged directly from experiments that refused to behave as classical theory predicted. At the center of this rupture stood Werner Heisenberg**, whose work revealed that the universe imposes boundaries on what can be known, not because of human weakness, but because of how reality itself is structured. Before this shift, measurement was assumed to be a neutral act. In classical physics, an object possessed properties: position, velocity, energy, whether or not anyone observed them. Measuring these properties simply uncovered what was already there. Errors were attributed to imperfect instruments or clumsy technique, and it was believed that with enough refinement, measurements could approach exactness. Knowledge, in principle, had no ceiling. Heisenberg's insight shattered this assumption. While analyzing the behavior of electrons inside atoms, he realized that attempting to measure certain quantities inevitably disrupted others. This disturbance was not accidental. It did not result from poor design or technological immaturity. It was unavoidable. The more precisely one tried to determine where a particle was, the less precisely one could know how fast it was moving. Conversely, pinning down its momentum blurred its position. This was not a practical inconvenience. It was a structural feature of nature. The crucial realization was that uncertainty was not about ignorance of pre-existing values. It was about the impossibility of assigning those values simultaneously in the first place. Position and momentum were not hidden behind a veil, waiting to be revealed. They were mutually exclusive forms of description at the quantum level. Reality did not carry both pieces of information at once in a definite way. The classical picture of particles as tiny billiard balls, each with a precise trajectory, simply did not apply. This conclusion struck at the heart of determinism. If the exact state of a system cannot be fully specified, then its future cannot be calculated with certainty. Classical physics depended on the idea that perfect knowledge of the present guaranteed perfect prediction of the future. Heisenberg's result made this impossible even in theory. The universe itself withholds the information required for absolute prediction. What made this especially unsettling was that the uncertainty principle did not depend on any particular interpretation of quantum mechanics. It was not a philosophical add-on or a matter of taste. It emerged directly from the mathematical structure of the theory and from experimental reality. The wave, like nature of particles, meant that they could not be localized without consequence. To confine a wave in space required a spread in momentum. This was not a trick of language, but a fact encoded in the equations. The act of measurement was thus redefined. Observing a quantum system was no longer like reading a thermometer. It was more like forcing a choice among possibilities. Measurement did not reveal a hidden truth. It participated in bringing about a specific outcome. The observer could not stand outside the system untouched. Interaction was unavoidable, and interaction had consequences. This deeply troubled thinkers who believed, like Albert Einstein, that physics should describe an objective reality independent of observation. From that perspective, uncertainty looked like an admission of defeat. If science could not say what exists before measurement, what kind of description was it offering? Was reality being replaced by statistics? Yet the power of Heisenberg's principle lay precisely in its refusal to be dismissed. Experiments confirmed it again and again. No clever workaround restored classical certainty. Even with idealized instruments and perfectly controlled conditions, the trade-off between complementary quantities remained. Nature itself enforced the rule. This led to a profound shift in how laws were understood. Instead of dictating exact outcomes, the laws of quantum mechanics governed probability distributions. They specified what was likely, not what was inevitable. This was not randomness without structure, but uncertainty constrained by precise mathematical rules. The probabilities themselves followed strict laws, even if individual events did not. Importantly, this uncertainty did not render the world chaotic or unpredictable at all scales. At the level of everyday experience, the effects average out. A baseball does not randomly teleport because the quantum uncertainties of its trillions of particles cancel one another. Classical certainty emerges as a large-scale approximation, not as a fundamental truth. Determinism survives, but only as a statistical illusion born of scale. The philosophical implications were unavoidable. If uncertainty is fundamental, then the universe is not a finished script unfolding frame by frame. It is a dynamic process in which possibilities play a central role. Events are not merely revealed, they are actualized. The future is not fully encoded in the present, even in principle. This realization forced science to confront limits it had never before acknowledged. There are questions that cannot be answered with arbitrary precision, not because science is incomplete, but because reality does not permit such answers. The demand for absolute certainty, once seen as the hallmark of good science, became an unrealistic expectation carried over from an earlier worldview. Heisenberg's contribution, therefore, was not just a technical result. It marked a transformation in the meaning of knowledge itself. Knowing no longer meant pinning down exact values, but understanding the range of possibilities and their probabilities. Precision was redefined. Accuracy no longer meant certainty, but consistency with the limits nature allows. In accepting this, physics did not abandon rationality, it refined it. The uncertainty principle did not say that anything can happen. It said that not everything can be known at once. The universe remained lawful, but those laws described a reality richer and stranger than classical intuition had prepared us for. What emerged from this shift was a humbler science, one that recognized boundaries not as failures, but as features. Heisenberg's insight forced humanity to accept that the quest for knowledge does not end in perfect clarity. Instead, it leads to a deeper understanding of why some forms of clarity are forever out of reach. In doing so, it transformed uncertainty from an enemy of science into one of its most profound revelations about the nature of the world. The tension between certainty and chance reached its most memorable expression in a single sentence that echoed far beyond physics. God does not play dice. With these words, Albert Einstein gave voice to a discomfort that many scientists and philosophers felt, but could not so neatly summarize. The statement was not an attack on mathematics or experiment, but on what quantum mechanics seemed to imply about the nature of reality itself. To Einstein, a universe governed by probability rather than necessity felt incomplete, as if the deepest layer of existence had been replaced by guesswork. Quantum theory, however, told a different story. As it developed through the work of physicists like Werner, Heisenberg, probability was no longer a temporary stand-in for ignorance. It became the final language of the theory. Electrons did not travel along single, well-defined paths. Instead, they were described by wave functions that encoded a spread of possible outcomes. The theory could not say where a particle was, only where it was likely to be found. When measurements were made, the results seemed to be selected at random, constrained only by statistical rules. This was the moment when the metaphor of dice entered physics. Dice symbolize blind chance. Once thrown, no law determines which face will land upward. To Einstein, this was unacceptable as a description of nature. He believed that the universe must have an underlying order that quantum mechanics had not yet uncovered. Probability, in his view, reflected our lack of knowledge, not an absence of causes. God, if the metaphor was to be taken seriously at all, would not leave the structure of reality to chance. Supporters of quantum mechanics argued that Einstein's objection misunderstood the role of probability. Quantum randomness was not lawlessness. The probabilities were calculated with extraordinary precision and confirmed by experiments to astonishing accuracy. The uncertainty lay in individual outcomes, not in the overall structure. In this sense, the universe did not behave like a reckless gambler, but like a system that followed strict rules while refusing to commit to a single outcome in advance. This distinction led to a deeper metaphor, not dice but cards. In a card game, chance is real, but it is not unlimited. The deck contains a fixed set of possibilities, and the rules determine how cards can be dealt, played, and combined. No player can predict the exact hand they will receive, but every hand is constrained by the structure of the game. Quantum mechanics, in this view, describes the deck and the rules, not the specific hand that will appear in each round. Under this interpretation, probability becomes a feature of reality rather than a flaw in knowledge. The universe does not decide outcomes arbitrarily. It selects them from a carefully structured range of possibilities. The laws of physics define what can happen and how likely each possibility is, but they do not dictate which possibility must occur. The future is open, but not chaotic. This shift had profound philosophical consequences. Classical physics suggested that the present fully determined the future. Quantum physics replaced that certainty with a branching landscape of potential outcomes. Events are no longer inevitable, they are actualized from among alternatives. Reality unfolds through choices constrained by law, but not fixed in advance. Einstein found this deeply troubling because it seemed to undermine the idea of an objective reality independent of observation. If outcomes are not determined until measurement, what exists before measurement? Quantum mechanics answered this question indirectly by refusing to describe unmeasured reality in classical terms. Instead of definite properties, it offered probability amplitudes. This was not a retreat from science, but a recognition that classical concepts were inadequate for describing the quantum world. The dice metaphor, therefore, was both powerful and misleading. It captured Einstein's sense of unease, but it also oversimplified what quantum mechanics was actually claiming. The theory did not say that nature was irrational or capricious. It said that certainty itself had limits. Where classical physics demanded exact answers, quantum physics offered distributions. Where classical theory sought inevitability, quantum theory described likelihood. Over time, experiments increasingly favored the quantum view. Attempts to restore determinism through hidden variables faced severe constraints, and many were ruled out by empirical tests. Nature appeared to embrace probability at a fundamental level. The dice, if they were being thrown at all, were weighted according to precise mathematical laws. The debate over dice and probability was never just about physics. It reflected a deeper human struggle with uncertainty. Determinism offers comfort, suggesting that the universe is fully intelligible and predictable. Probability challenges that comfort, insisting that some aspects of reality remain open and unresolved until the moment they occur. Quantum mechanics forced science to accept this openness not as a temporary inconvenience, but as a defining feature of the world. In the end, the universe revealed itself as neither a rigid machine nor a chaotic gamble. It follows rules with extraordinary precision, yet it allows room for chance within those rules. Whether one prefers to imagine God playing dice, cards, or neither at all, the lesson remains the same. Reality is governed by laws that do not always deliver certainty, and in that uncertainty lies one of the most profound insights modern physics has ever uncovered. To understand why metaphors like dice and cards became central to debates about quantum physics, it is necessary to recognize how deeply language shapes our understanding of reality. Physics does not only rely on equations, it also depends on images and comparisons that allow abstract ideas to become thinkable. When classical physics dominated, the preferred metaphors were machines, clocks, and gears. These images reflected a universe that ran smoothly, predictably, and without surprise. Every motion followed from a prior cause, and nothing essential was left to chance. The metaphor of dice entered the conversation as a provocation. When Albert Einstein rejected the idea that God plays dice, he was not making a theological statement, but a philosophical one. Dice represent pure chance. Once thrown, no hidden order determines the outcome. The result is fundamentally unpredictable, even in principle. To Einstein, accepting dice at the foundation of physics meant abandoning the idea that reality is fully governed by reason. It implied that the universe at its deepest level does not care about explanation. Quantum mechanics seemed to invite exactly this conclusion. The theory described particles not as objects with fixed properties, but as probability waves. It could predict the likelihood of outcomes with stunning precision, yet it could not say which specific outcome would occur in any single event. An electron hitting a detector appeared to choose its position randomly, guided only by probability. To many observers, this looked indistinguishable from a dice roll. But this impression was misleading. Dice are simple objects governed by classical mechanics. Their randomness arises because we lack complete information about initial conditions like force, angle, and surface texture. In principle, if every detail were known, the outcome of a dice throw could be predicted. Quantum randomness is fundamentally different. It persists even when all possible information is known. The unpredictability does not come from ignorance. It comes from the structure of reality itself. This is where the metaphor of cards becomes more illuminating. A deck of cards contains a fixed set of possibilities. The rules of the game strictly constrain what can happen, yet the specific hand a player receives cannot be predicted in advance. Chance is present, but it operates within a tightly regulated framework. The randomness is real, but it is not unlimited. Quantum mechanics resembles a card game more than a dice throw. The laws of physics define the deck, the allowed states, the possible outcomes, and the probabilities associated with each one. Nothing outside the deck can occur. Nature does not invent new cards mid-game. However, which card is drawn in any given moment is not predetermined. The outcome is selected from among the allowed possibilities when an interaction takes place. This distinction matters because it reframes the role of probability. In a dice game, probability feels crude and final. In a card game, probability feels structured and meaningful. The game has order even though its outcomes vary. Quantum mechanics operates in this second sense. It is not chaotic, it is disciplined. Its uncertainty is mathematical, constrained, and reproducible across experiments. Physicists like Werner Heisenberg understood this intuitively. The uncertainty principle does not say that measurements are sloppy or outcomes arbitrary. It says that nature limits how much information can exist simultaneously. The hand dealt by the universe cannot contain every card at once. Some pieces of information exclude others, and this exclusion is built into reality. The card metaphor also helps clarify why quantum mechanics still produces a stable world. At large scales, countless quantum events combine. Individual uncertainties cancel out, much like the randomness of individual card draws becomes irrelevant over many rounds of play. This is why everyday objects behave predictably, even though their constituent particles do not. Classical certainty emerges as a collective effect, not as a fundamental truth. Einstein resisted this interpretation because it seemed to remove necessity from the universe. Cards, after all, allow for multiple futures. But this openness may be the point. Quantum mechanics suggests that the universe is not a single, locked path unfolding from the past, but a system in which multiple futures are genuinely possible until one becomes actual. The laws do not dictate events, they constrain them. Seen this way, the universe is not gambling recklessly. It is playing a sophisticated game with strict rules and limited options. Chance operates, but it operates lawfully. The randomness is not a flaw to be corrected by a deeper theory. It is a feature to be understood. The enduring power of the dice and cards metaphors lies in what they reveal about human expectations. Dice offend our desire for meaning because they suggest blind chance. Cards are easier to accept because they preserve structure alongside uncertainty. Quantum mechanics ultimately aligns with the second image. It does not abolish order, it redefines it. In accepting this, physics moved beyond the idea that explanation requires inevitability. Understanding no longer means predicting every detail, but grasping the space of possibilities and the rules that govern them. The universe, according to quantum mechanics, is not a machine that must unfold in one way only. It is a lawful system that allows outcomes to emerge from probability, not because it lacks order, but because its order is deeper and more subtle than classical certainty ever allowed. The debate ignited by quantum mechanics did more than reshape physics. It fractured the very meaning of reality that Western science had relied upon for centuries. Before this rupture, reality was assumed to be something fixed, external, and fully formed, existing independently of observers. Objects had properties whether anyone measured them or not. Science's role was to uncover those properties, layer by layer, until the true structure of the universe stood revealed. This assumption was so deeply embedded that it was rarely questioned. Quantum mechanics did not simply challenge it, it dismantled it. At the heart of this rupture was the realization that observation could no longer be separated from what was observed. In classical thinking, the observer was a spectator. In the quantum world, the observer became a participant. Measurement was not a neutral act, it was an interaction that helped define the outcome. This was not a matter of human consciousness influencing reality, but of physical interaction itself. The tools used to measure a system inevitably altered that system, and this alteration was not accidental, it was fundamental. This idea struck directly at the realism defended by Albert Einstein who believed that physics should describe what exists, not merely what is measured. To Einstein, the suggestion that particles lack definite properties until observed felt like a retreat from objective reality. If physics could only speak about probabilities and outcomes of measurements, what happened to the world itself? Was reality being reduced to a set of experimental results? quantum mechanics answered this challenge in an unexpected way. It refused to describe unobserved reality in classical terms at all. Instead of trajectories, it offered wave functions. Instead of definite properties, it offered probability amplitudes. These mathematical objects did not represent things in space and time as classical physics did. They represented potentialities, structured possibilities that could become actual under the right conditions. Reality, at its most basic level, appeared to exist not as a collection of facts, but as a spectrum of possibilities. This shift transformed the meaning of physical law. Laws were no longer commands dictating exactly what must happen. They became constraints defining what could happen and how likely each possibility was. The universe stopped being a script already written and became more like a process unfolding in time. The present no longer fully determined the future. Instead, the future emerged from a range of allowed outcomes. Physicists such as Werner Heisenberg understood that this was not a failure of description, but a discovery about nature itself. The limits imposed by quantum mechanics were not gaps waiting to be filled by better theories. They were boundaries that defined the structure of reality. Asking for more precision beyond those boundaries was like asking for a square circle logically incoherent within the framework of the world. This new picture unsettled not only scientists but philosophers. If properties do not exist in a definite way before measurement, what does it mean to say that something is real? Quantum mechanics forced a distinction between reality as potential and reality as actual. Before interaction, systems exist in a state that cannot be fully captured by classical language. After interaction, one possibility becomes actual, and the others vanish. Reality, in this sense, is not static, it is event-based. The rupture also challenged the notion of completeness. Classical physics aimed for a final, all-encompassing description of the universe. Quantum mechanics suggested that such completeness might be impossible. There may be no single, observer, independent description that captures everything at once. Different experimental setups reveal different aspects of reality, and those aspects cannot always be combined into a single picture. Complementary descriptions replace unified certainty. This was deeply unsettling because it undermined a long-standing faith in total explanation. The idea that science might face principled limits, not temporary ones, felt like a betrayal of Enlightenment ideals. Yet quantum mechanics did not abandon reason, it refined it. It showed that demanding classical clarity from a non-classical world was a category mistake. The problem was not that reality was irrational, but that human intuition had been trained on the wrong metaphors. Over time, this philosophical rupture reshaped how science understood itself. Objectivity no longer meant detachment from the system under study. It meant reproducibility within clearly defined experimental contexts. Truth became contextual rather than absolute, without becoming arbitrary. Reality was still real, but it was not obligated to conform to classical expectations. The legacy of this rupture is still unfolding. Quantum mechanics forced humanity to confront a universe that does not offer certainty as a default feature. Instead, it offers structure without inevitability, law without prediction, and reality without full disclosure. In doing so, it did not weaken science. It deepened it, revealing that the search for truth sometimes leads not to firmer ground, but to a more convincing understanding of why the ground itself can never be completely solid. The consequences of the struggle between determinism and uncertainty did not end with philosophical debate. They reshaped the entire trajectory of modern science and quietly transformed how humanity understands its place in the universe. What began as a disagreement between towering figures such as Albert Einstein and Werner Heisenberg evolved into a new scientific world, one whose effects now reach far beyond theoretical physics. One of the most profound outcomes of this shift was the realization that uncertainty is not an obstacle to progress, but a resource. Technologies that define contemporary life are built directly on quantum principles that once seemed philosophically troubling. Semiconductors, lasers, magnetic resonance imaging, atomic clocks, and emerging quantum computers all rely on probabilistic laws. These technologies work not despite uncertainty, but because of it. Engineers learned to design systems that exploit probability rather than fight it, turning what once appeared to be a weakness into a source of power. The acceptance of quantum uncertainty also changed the goals of science itself. Classical physics pursued exact prediction as its highest ideal. Quantum physics replaced that ideal with statistical mastery. Success no longer meant knowing exactly what would happen in a single event, but knowing the distribution of outcomes across many events with extraordinary precision. This redefinition of knowledge proved to be not a retreat, but an expansion. Science gained predictive power precisely by letting go of the demand for certainty in individual cases. This transformation extended into philosophy and culture. The idea that the future is not fully determined by the past challenged long, held assumptions about fate, causality, and control. While quantum mechanics does not grant free will in any simple sense, it undermines the notion that the universe is a closed system unfolding with mechanical inevitability. The future, at least at the fundamental level, is not entirely written in advance. It emerges through a process governed by law, but open to multiple outcomes. Importantly, this openness did not lead science into mysticism or relativism. The probabilistic laws of quantum mechanics are among the most rigorously tested in human history. Their predictions are precise, repeatable, and mathematically exact. What changed was not science's commitment to objectivity, but its understanding of what objectivity means. Objectivity became tied to reproducible outcomes within defined conditions, not to detached observation of a fully determined reality. The legacy of Einstein's resistance also remains essential. His refusal to accept probability without protest forced physicists to confront the foundations of their theories rather than treating them as mere calculation tools. Debates about realism, locality, and completeness sharpened the conceptual clarity of quantum mechanics. Even when Einstein's preferred answers were not adopted, his questions shaped the direction of research for decades. Modern discussions about quantum information entanglement, and the nature of measurement still echo his concerns. At the same time, Heisenberg's contribution redefined intellectual humility. The uncertainty principle taught science to recognize limits without interpreting them as failure. There are questions that cannot be answered with infinite precision, not because knowledge is lacking, but because the universe does not contain those answers in the form we demand. This realization introduced a mature view of understanding, one that distinguishes between what is unknowable in practice and what is unknowable in principle. Perhaps the most enduring impact of this shift is psychological rather than technical. Humanity learned that the universe is not obligated to align with human intuition. The demand for certainty, so effective in everyday life, becomes a liability when imposed on the foundations of reality. Quantum mechanics revealed that nature is subtle, not simplistic, and that deep order can coexist with genuine unpredictability. Today, the phrase "God plays dice" is no longer a scandal. It is a shorthand for a deeper truth, that the universe operates through laws that allow chance without surrendering structure. Whether one prefers metaphors of dice, cards, or mathematical waves, the lesson remains the same. Reality is not a rigid machine grinding forward along a single path. It is a lawful system in which possibilities are real, outcomes are selected, and the future is shaped rather than predetermined. This legacy continues to influence how science approaches the unknown. Instead of demanding final answers, modern physics accepts provisional descriptions, multiple interpretations, and principled limits. The goal is no longer to eliminate uncertainty, but to understand its role. In that sense, the debate that once divided physics ultimately enriched it, leaving behind a world that is less certain, more flexible, and far closer to the strange, elegant behavior of universe itself.